Thank you everyone for being here. It's a pleasure to have Ludger Wirtz with us. Ludger is a professor in physics in the University of Luxembourg, and I've known him for basically forever. And he did his PhD with Blaha, right? In Vienna.
Okay.
I learned something more today. And then we met when he was postdocing in San Sebastian with Rubio, to which he got a CNRS position in Lille, in IEMN, on things related to spectroscopy and semiconductors in a big center for more applied technology. And then in 2016, 12, he was appointed professor in the burgeoning university in Luxembourg, which has grown quite a bit in international visibility since then, thanks to you, of course, and thanks to a lot of very important international hires. So Ludger is well known in the fields of spectroscopy, electron-phonon coupling, phase transitions, a number of other things. And today he'll be telling us about excitons in particular, so optical properties of matter and the symmetry consequences of how these are constructed in crystals.
Okay, thank you very much, Matthieu, for this kind introduction. And yeah, indeed, I have been here maybe 16 years ago, visiting Wannier with Christoph Dilute, and we were working in this European project. So it has been quite some time. And at that time, Selina and Matthieu were not here, and now they are. So, time I visit you here in Utrecht at the occasion of the thesis defense. We cover tomorrow. And yeah, it's a pleasure to talk about one of my favorite topics, which is excitons. And recently we started to look more in detail at the symmetries of excitons. And that has been the main part of the thesis of my former PhD student, now postdoc, Muralidhar Nalabothula, who finished his thesis this year in spring. And I put him in bold because I am essentially using his slides yeah, try to guide you through this talk. The other collaborators have been Sven Weichert, a long-time postdoc in my group in Luxembourg, and there have been further contributions by Fulvio Cagliari at the CNR in Modena and Davide Sangalli's CNR Rome. And what you see on this picture is an exciton in layered boron nitride. And if you do not yet understand this figure, don't worry, because we will start with the explanation, what is an exciton? And a simple answer to this is that an exciton is like a hydrogen atom in a solid. So that's a very, very simple picture. You know that in a solid semiconductor, you can create excitations by taking an electron out of the valence band and putting it somewhere in the conduction band. And then you have a hole left behind in the valence band and an electron being attracted to this hole. So in the best case, they form like a hydrogen-like state. And we can use the good old Schrödinger equation to calculate the energies of excitons. And that would be then this picture here, that you have different excited states, the ground state, S state, and then the orbitals, and so on. So that would be then, if it was true that the electron and hole are just interacting with their respective masses, and that we get these hydrogen-like states, then we would easily obtain the energies. And we could also discuss how an exciton interacts with light. That we also know from physics. We have ground state, arbitrary state defined by its quantum numbers, and then you try to excite it to another state to find quantum numbers. So you calculate dipole matrix element, and whenever this is not equal to 0, you may have some absorption. And then you can write dipole selection rules, and it's important that you switch the parity of the state because dipole operator is uneven and inversion, and so in order for this matrix elements not to be 0 a priori, you have to switch the parity. So it could be very easy because we know everything from atomic physics. We just need to remember it, and I will be done with my talk. Of course, the exciton in a solid is not so simple. So the reality, or at least the reality in my calculations, if I, which I think is true nevertheless. Anyway, this is an exciton in monolayer boron nitride. What I plot here is a so-called excitonic wave function. So if the hole is located on the central atom, which would be a nitrogen atom, because the valence and maximum of that orbitals. So if the hole is located there, then this figure expresses the probability density to find the electron bound to that hole. And we see that it's mostly located on the nearest neighbor atoms. So it is very strongly bound. So clearly, this exciton feels very much the atomic granularity, the crystal structure of the underlying material. So we are far from this Wannier-like picture where the electron is several or maybe several tenths of atomic distances apart. No, it is very confined. So we do not have a full rotational symmetry that you have when you investigate the symmetry of a hydrogen atom. We have rather the space group symmetry of the underlying crystal that we have to take into account when we analyze the symmetry of X. That's, of course, very well known for quantum chemists. You have the habit to always analyze the symmetry of their states. It has, it is in principle known as solid state physics, but surprisingly, up to now, there has been a little work on the analysis of excitons. So on the theoretical level, how do we calculate excitons? So let's start with this picture of a typical band structure in a semiconductor or insulator. So we have the valence band maximum and the conduction band minimum. And in a simple picture, you would have independent electrons that you excite to the conduction band, and you would have independent holes left behind in the valence. So in that case, absorption would be possible at all vertical, or you would also see non-vertical transitions in the Brillouin. Now, since the electron and the hole are interacting, you will not only have the independent electron hole pair excitation, we have an electron hole interaction kernel. That's basically the Coulomb action, Coulomb interaction between the negative electron and the positive hole. And they lead, well, also it's a screen Coulomb interaction, sorry, put it on the slide. But since we are in a dielectric environment, the interaction is weaker than vacuum. But that doesn't change the fact that we have an attractive interaction between the electron and the hole. And this leads to a mixing between different states, between different transitions. And this then gives rise to excitonic states that have different energies. We can have discrete states in the band gaps, very close to the moment. And then our exciton can be written as a linear superposition of holes and excited electrons. And those coefficients are the so-called exciton eigenvectors. So let's see how this works for a prototype example. Hexagonal boron nitride, the layer of it. So here you have the hexagonal crystal structure and the nitrogen boron atoms. And I show you the band structure, which is composed of the pi z orbitals, the orbitals perpendicularly sticking out of the layer. And I also show you that one can easily fit them in a simple tight binding model, which we did some years ago. And you will see in a moment why we did it. In principle, you see that the band structure is confined around the high symmetry point K. So that's the edge of the hexagonal ring. And so to zeroth order, we can describe it as a parabolic dispersion around this state. So now let's look at the absorption spectrum. So the band edge, did I put the scale? Yeah, the band, so the absorption onset would be somewhere at 7 electron volt. That is the band gap. But you see that there is nothing at 7 electron volts. There is a very strong peak at 5.5, and then there is a couple of other peaks. So it's like a hydrogen-like series of excited states, some of them which are bright and some of which are not. So the first one corresponds to this very strongly, very tightly bound exciton, whose wave function I've shown you on the second slide. And then you see.
Quick question here. Because when you mentioned this the last time, you said that the hole was localized in the center, but was that actually an eigenstate that was there? And because it's not, I mean, from here you see that these are smoothed out orbitals. So when you say that the hole is sitting on one atom in the center, you actually mean that it's just sitting on that orbital.
Yes,
out as well.
Exactly.
Just so that
In principle, that's a very good question. In principle, the exciton is also an extended object, like a phonon or any quasi-particle. But in order to, and I have a 6-dimensional wave function, 3 coordinates for the hole, 3 coordinates for the electron. So in order to describe the interaction between the electron and the hole, I decide to fix the hole somewhere. In one particular Brillouin zone, or one particular position within the infinitely extended crystal, and within this unit cell on one particular orbit, on one particular F. This wave function changes if I put the hole somewhere else.
But let's say that you could also, for instance, plot the, let's say, the density of the particle and the density of the hole on top added together, kind of, would the image still look very similar?
Well, we have been a long time discussing in the group how to best plot the wave functions. I mean, yes, you could do this, and you will later on see that I do a sum over different positions of the hole for symmetry reasons. You could also try to integrate over all possible positions of the hole. The result is not always visually convincing. As long as you know what you are doing and don't interpret it don't put too much in it. It's a valid way, but I agree, one may ask questions. So let's just look at the wave functions and do a little bit of atomic physics. So this could be also an atomic-like absorption spectrum, where you do then where you have a Rydberg-like series of states, and you know from atomic physics, the higher your energy, the more nodal lines you have in the wave function. Well, the wave function is there, so you don't see it so much, but in principle, you expect more nodal lines, and you expect the wave function to become more and more extended, as you see is the case here. Also, you see that some states are bright, sometimes are dark, some are dark, and but in the initial calculations you do not really see this. So that's why at the time in the 2016, now the PhD thesis by Galvani, we did a simple tight binding model and discussed symmetries in the tight binding. In tight binding, you have kind of localized atomic-like basis. That's why we could also plot the wave functions itself. And then you get the sign, root for positive and red for negative, or the other way around. And then you can do mirror images, and then you see that those wave functions are even or odd. What we also did at the time, we were plotting the wave function in a reciprocal space.
Can I ask a question? The dark states, if it's due to algorithm not matching or is it not complex? Or you come back on that?
I come back on that because that's one of the results. Here up to now, you can just understand it in terms of even or odd. Yeah, here we are plotting the wave function in reciprocal space. So when we do our, maybe I come back to this one here. When we calculate the wave function, so you see that we are mixing transitions at different wave vectors. And in this figure here, we just plot in the first Riemann zone, which happens to be hexagonal. We just color all the k vectors where we have a lot of transitions corresponding to a particular excitonic state. And you see that we are coloring the corners of the hexagon. Those are the high symmetry point k at the edges of the hexagon. And yeah, there you also see a nice figure. At the moment, just enjoy the nice colors. If we have so-called S-like states, then there is only one color at each corner. And as you go around all the 6 corners, you go, but you have a phase of 2 pi that you cross. And then you have 2 degenerate excitons. In one case, it's those 3 corners that are contributing, and for the bright exciton, it's the other 3 corners. That's, you have 2 degenerate excitons related by time reverse symmetries going from k to k to minus k or to k. For the so-called p excitons, you are crossing, you have a phase shift of 2 pi as you go around the corner of the hexagons once. So, to summarize here, for all states, we have a phase that rotates by 2 pi over 3 when you move between 2 equivalent K points. Or states with S-type, and we know you have a constant phase around a given K point, and for states it's a p-type envelope, you have a phase rotation around each of those phases. So those were kind of ad hoc observations that we made when we analyzed more in detail the results of our calculations. And now in this talk, I try to give you a more systematic assessment of exciton symmetries. So let's look at a particular exciton with the called S at a certain finite momentum Q. So this exciton is composed of electrons with a wave vector K, and then the corresponding pole has a wave vector K minus Q. Or do it the other way around, call it K and C K plus Q. Doesn't really matter. Just if we do this analysis for excitons with a finite momentum, then electron state or state have a different vector. And then we do a sum over all conduction and valence bands. For quite it's enough to just use the highest valence band and lower conduction band. And we do a sum of the principal in integral over the whole Brunel zone. I write sum because we call it a finite K-point sampling, giving us the sum. So now the question is, if we do a symmetry operation that obeys the space group symmetry of the crystal, how would it act on the X? Now I could talk a long time about space group symmetry, how you divide it into the translational part and the so-called point group symmetry of the crystal. Here it should be enough to say that, okay, you have a rotational part or a discrete part, which can be a rotation or a point group operation. So one point of the crystal remains invariant. So it's rotations or reflections or inversions. But you can also have a translational part. There are the so-called non-symmorphic symmetries where you do a rotation followed by a fractional translation mapping back to itself. So you need both parts in order to describe a symmetry operation in your crystal in the most general sense. So assuming that our symmetry operations can be described by an operator U of R, then taking your original symmetry, your original exciton, and having the operation U acting on both the hole and the electron part, you obtain the new the rotated or symmetry transformed exciton. And you can also write this in matrix form, and then you get the transformation matrices represented by the calligraphic D. I don't want to go too deeply into the theory. I would rather give you an idea how we use this formalism to actually symmetry or analyze the resulting symmetries of our excitons. So imagine that you apply translation to an exciton and then applying this translation basically means that we take our original exciton and we get a phase e to the minus I r cubed times that is vector A. And with that, you get back the same exciton, just translated by a discrete less compatible distance. So that's nothing special. It basically gives us a new phase. And keeping phases is important when you do exciton-phonon coupling, and when you have to integrate over excitons in the full. So why are we so picky about the phases? Well, you see here a square lattice, but also view it as a reciprocal lattice, and then you do not want to calculate excitons in the full Riemann zone. You just would like to calculate excitons in the irreducible part of the Riemann zones, and then by using symmetry operations on the excitons, you can expand the excitons to the full Riemann zone and keeping the proper phases. So the same holds when we do this time we do a rotation. Here we are in reciprocal space, so we rotate our Q vector, and well, we may go to a different, to a higher Riemann zone. So a rotation might be a rotation plus a translation by a lattice vector of reciprocal space. And with that, we can again calculate the matrices U of R, and if our exciton is composed of independent electron-hole pair transitions, we can calculate the transformed exciton. So far, this is only theory, and well, let's now go towards the application. Because now, if we take all point group operations that belong to the so-called little group, so what is a little group? It's not a full space group. It's a space group modulo the translations, and the little group is different for every wave vector within the first plane. Example later on when I come to this right. At the moment, let's just accept that there is a little group that corresponds to a certain Q vector, and for example, it might be the C3 group. There you have the unit operation, 3-dimensional rotation by 120 degrees, and then 2 times 120 degrees of those 3 operations, and calculate the multiplication table and the corresponding character table, and then do your symmetry analysis according to this character table. So let's look at the first example, bulk boronitride. Seen the single layer boronitride. Now let's take infinite stacking of that, and the little group at the gamma point for vertical excitation. We have the full point group of the crystal, and that is the 6H. So we have the 6-fold rotational axis, horizontal mirror symmetry, and planar symmetries, and we have a corresponding character table. And when you calculate the absorption spectrum, you see a peak at 6.2, a smaller peak at 6.55, and a few more even smaller peaks at higher energies. But if you really look at the eigenvalues of the Bethe-Salpeter Hamiltonian, then you see that there are many more different states. And with the code implementation of Muralidhar, you see that you get not only the list of exciton energies that codes like Jumbo or Bus or exciting or Berkeley W have been delivering up to now. Now, for each exciton mode, we also do the symmetry analysis, and we get the symbol of the underlying symmetry class. And then you see that it's the E1U exciton, only the E1U excitons that are bright. And why is that? I just go to the internet, look at the corresponding character table of the point group P6H, and then you look for all symmetry classes that transform like linear functions, xy, and then it's only the E1 state optically active. And all the others are simply dipole poles. So we can do the same with bulk lithium fluoride. Lithium fluoride, like sodium chloride, has a rock salt structure. So the point group is OH, highly symmetric. We have many symmetry operations, and the higher the symmetry, the more strict are the selection rules. And in particular, since it's an octahedral group, we also get triply degenerate excitonic states. A and B are usually non-degenerate symmetry classes. E stands for a two-dimensional subspace, and T stands for states that are threefold degenerate. And again, you look out which one is optically active, and then you find that it's T1U states that are optically active. And indeed, if you just calculate your absorption spectrum again, you see peaks at positions of T1U excitons and nothing in between. And now let's look at the symmetry of the states. And here we are back to the wave functions. And again, we look at a rather peculiar way of plotting those wave functions. So here we are actually not plotting the density of the electron, but we are plotting the density of the hole. So here we determine the position of the excited electron, and we say it's localized in a 1s orbital of a lithium atom. And since the 1s orbital is peaking at the position of the nucleus, we can actually put the electron really on top of the, or at the nucleus of a lithium atom. And why are we doing this? Because we would like to keep the symmetry of the crystal. So if we have the electron at one of those atoms, then the symmetry of the wave function of the whole probability, the probability amplitude of the whole should be symmetric with respect to the crystal point group. And indeed, what you see here is the 3 degenerate T1U excitons that are responsible for the main peak in the absorption spectrum. And it's a little bit tilted, that's due to the finite resolution and the plot exciton wave function. But basically, you see that this exciton here is this one here rotated by 90 degrees, and this one is when you rotate it by 90 degrees out of it. So it's like pretty much like the px, py, and pz orbital of the hydrogen atom that are pointing along the 3 Cartesian axes, with the exception that here we may be pointing along the z-axis, but here in the xy plane we are rotated by 45 degrees with respect to the crystal axis. But since the 3 excitons are degenerate, we could just rotate them, so we could find a completely Cartesian basis of the 3 degenerate excitons in the xyz directions. So here we come to the exciton dispersion in lithium fluoride. I told you that we have to always analyze according to the little group, or the twice group, of the corresponding Q vector. Possibly I didn't have enough time, but today also to really prepare more pedagogic slides on this. So, but let me walk through this analysis. So far, we have looked at excitons at the high symmetry point gamma. Q is equal to 0. So the fact that we have a wave vector will not destroy, if you want, the high symmetry of the crystal. Now assume that you have a finite Q, a wave vector, pointing along one of the crystallographic directions of your cubic lithium fluoride crystal. Then, of course, you will destroy the mirror symmetry in the direction of the wave vector. And you may destroy some other symmetries on the way as well. So if you now go to a finite wave vector, you have a lower symmetry group than at gamma. It turns out that at the edges of the Lumiere zone, at the point L or X or W, you still have relatively high point group symmetries. You even have a 3-fold rotation symmetry axis, but that if you go along the spatial diagonal of the cube, if you look at the cube on top of one of the edges, then you notice that it has a 3-fold symmetry, and that is reflected in D3D at the high symmetry point L. So then, our code now, doing the symmetry analysis of the excitonic wave functions, gives us the corresponding symmetry class for each finite Q exciton. And where do we leave that? That brings me to the last part of my talk, where we now apply this to understand something more complicated than just absorption. Let's go to luminescence, and let's go to luminescence in materials with indirect band. And the common knowledges assume that we have here such a conduction band structure where the indirect band gap is clearly lower in energy than the direct band gap. So what happens in the independent particle picture is that you get an absorption. Now we pump it with a laser, pump pulse, pump probe, or steady state laser. So you will pump electron hole pairs at gamma, meaning vertical optical excitations. But then your electron will go from this local minimum to the global minimum of the conduction band. And From it will go there via electron-phonon scattering. And from there, eventually, it wants to decay back to the hole left at the valence band maximum. But it can do so only if something takes over the finite momentum. And this something is, in this case, a phonon with finite wave vector P. So, what we have then is an intensity that depends on the temperature by the Boltzmann factor. But what is important here for us is the matrix scattering element, namely that which brings us from the finite wave vector exciton S Q equal Q to back to the exciton at 0. And then it can decay. So it is matrix that plays a role when you calculate a phonon-assisted luminescence. And for this one, there exist selection rules, which have been kind of observed in this paper where my group was also involved, but which was not properly analyzed, and there are different code implementations until now, which may or may not respect the selection. So let's see what happens. So here you see the exciton dispersion of boron nitride, of wild boron nitride, and you see it's an indirect band gap material, so it's not the exciton at Q equals 0, which is highest in energy, but it's the exciton with the wave factor at the point omega, which is roughly halfway between gamma and the H-cross. And we do the full symmetry analysis of excitons along this way. So if we excite an exciton at Q equals 0, we do it with it's an E1U exciton, the one that is dipole allowed. And now we would like to calculate the probability to go from there to the finite Q corresponding to omega. And we go there by exciton-phonon scattering. So you get some matrix element between your exciton and the finite Q exciton, which is given by the deformation potential induced by the phonons. Roughly, you are displacing the atom from their equilibrium positions according to a certain phonon mode. And this gives you a perturbation potential, which then renders this matrix element non-zero or not. So, just to give you a simple example, since all those excitonic states, the E1U and the A1 B1 at finite Q, are even under horizontal mirror symmetry, meaning when we do a reflection along a horizontal plane, then we map the exciton back onto itself. So if that is the case, then our perturbation potential should also be even under horizontal mirror symmetry. Otherwise, it will give the zero matrix. And as it turns out, if you look at the phonon modes, then you see that the in-plane modes, the LO, longitudinal, optical, or longitudinal acoustic modes, are all even under reflection, and the out-of-plane modes are not. How do you see this? Here you have a visualization. The arrows give you the displacement or velocity, and here, when you do the mirror reflection, you map the phonon mode onto minus itself. The upwards pointing arrows are matched on the downward pointing. And that's why for the phonon-assisted luminescence, if you look at the phonon dispersion of boron nitride, you just have the black modes that are coupling to finite Q excitons as they are optically excited. Between the out-of-plane modes are not covered. And if you don't believe me, you can go yourself to this phonon website that we did some years ago, and that is also available. Materials Cloud and other platforms. So you go to the dispersion, you click on it, and then you get the corresponding phonon mode. Here I'm plotting the one that corresponds to this mode here at the point omega, and then you can stop the movie, rotate the wave function, and verify indeed that it's even or odd. Or you just calculate the result with quantum espresso, and the quantum espresso tells you what symmetry class this phonon mode has. Yeah, I just told you how to look at symmetries of phonons. You can actually visualize the phonon modes, turn the material, and just look on how the phonon eigenmode maps onto itself. You can do something similar with the excitonic wave functions, but in this case, it's a little bit tricky. That comes back to the question of Michael. Where do you put the hole? In principle, we have a 6-dimensional wave function. So our numerical recipe gives you a full description of how to analyze the symmetry. If you want to do it visually, you have to think carefully where to put your hole. Boron nitride has a valence band consisting and conduction band consisting mostly of pz orbitals. So obviously we have to put the hole into a pz orbital of a nitrogen atom. Pz orbital has a nodal plane at z equal to 0. So we cannot put the hole at the position of the nucleus. We have to put it a little bit higher or lower. But by putting it higher or lower, we are breaking the symmetry of the crystal. For that, we have to put the hole twice, a little bit above and a little bit below. And then we have to think carefully if the whole wave function is even or odd. In this case, it's odd. And then we are subtracting the two probability amplitudes from each other. And what I've got here is then the corresponding wave function, which is the probability density, but with the phase positive or negative, then we try to choose the colors and then see if the wave function is even or odd. So there is a pictorial way of analyzing symmetries. It's not extremely straightforward, but it's doable. And then, if you just calculate the phonon-assisted luminescence, not the new result, but newly calculated. So here you see that you have 4 phonon peaks, 4 phonon sidebands, if you want, that constitute the luminescence signal of boron nitride. It's corresponding to the 4 allowed phonon modes. And then there are the out-of-plane phonon modes that in some calculations have given a different peak, small but non-vanishing. But now, just properly symmetrizing the excitons, this peak is exactly equal to 0 at its. And well, there is another form of boron nitride, which is rhombohedral boron nitride in C-stacked, where there is no horizontal symmetry plane. In this case, the selection rules are less strict, and those experimental results, as well as theoretical calculations, give you a small non-vanishing peak for the out-of-plane optical phonon. And that brings me to the conclusion. So we have implemented honest, my PhD student has implemented an Abelian method to compute irreducible representations of excitons. It's available in a beta version of Yambo and Pi. It's a module called Let's Electron-Phonon. Let's stand for Luxembourg. There is Let's Cola and Let's Chips and Let's Phonon coupling. Okay, so this allows us also to calculate excitons only in an irreducible wedge of the Brunel zone and expand it to the full wave function, and then you can do exciton-phonon coupling. With phonons also calculated irreducible zone and being expanded. And then you can do proper calculations of optical spectroscopy that involves coupling of excitons and phonons, such as the Raman spectroscopy and phonon-assisted luminescence spectroscopy. And yeah, acknowledgement, the really person did it. It's about not listed here, but I was taking the slide. So Muralidhar, and then the other people involved here. And yeah, using quantum espresso for the wave functions and Yambo Pi for the development. With that, I thank you for your attention. And
I should share myself. This is a nice case where it's polar and you know where to put the hole. But what about things like TNDs or things that are much less clearly divided, or where the orbital character is not well defined or unique? What do you do then for the position of an adapted recipe for different types of bonding or something like that? Look at the external function.
well, to be honest, my PhD student refused originally to do it. He said, I don't like it because in any case, it's cooking. So, there is no general recipe. So the only thing that
If
is
you want a single position for the whole, I agree. It's got to be some cooking, but there must be some symmetry adapted, like ideal representation, downfolding from 6 to 3 dimensions, so humans can actually look at it and not just him.
yeah. So the point is the higher your symmetry group, the more positions you might have to take.
Yeah.
Take lithium chloride. Okay, we were lucky we could put the whole the electron at the nucleus of lithium ion. But if you cannot do it because your wave function is consisting of d orbitals, you have to put it somewhere else in an off-symmetric position. So you might need up to 8 or maybe even 16. I guess 12 is the highest, or yeah, 12, depending on your symmetry. Position symmetry equivalent positions of the whole to add up the wave function. You can do this, but you have to decide on a case-by-case basis. And you may, so there is no automatic way so far of doing that. What is automatic is the mathematical symmetry analysis. That just depends on the character tables, get transformation matrices, analyze the character and consensus. That is general. I don't claim at the moment that we have the general way of representing the exciton wave. I forced Muralidhar to calculate them, at least for some examples, because that's
Nice picture.
nice pictures. And I think you can learn something from it, but it's the physics in it is in.
Yeah, I mean, it's since we ended up in this direction anyway. Can you say something about the entanglement between the electron and the hole? Because you could have the electron and the hole essentially just being, say, the determinant constructions. One is sitting in one state, the other one sitting in the other state, or you have actual entanglement between them, and depending on where the hole is, the electron will be somewhere else. Do you have any intuition or this is something that is interesting, reasonable to look at.
But I mean, we are always in this, if you want, single Slater determinant picture, right?
Right.
But
The reason I'm asking is if you're always in the single state determinant picture, then you can just visualize the whole and the electron separately because they don't solve each
I don't think if you're in the VSC, if you solve the VSC, you don't have a single Slater determinant, right? It's compositions of transitions, each of which corresponds to a different Slater determinant. So you have the
no, sure. Sorry. Yeah. Okay. Yeah. It's a sum of single Slater determinant. We have two single excitations. So we take the ground state wave function. It always it corresponds to configuration interaction with single excitations. To be precise. Yeah, but still we cannot, I mean, there is no, I mean, of course, you can, if you want, you can integrate out the position of the whole, and then represent the integral over all the corresponding electrons. We didn't do this, I'm afraid that.
I'm perfectly fine with this being hard, right? That's not the problem. I mean, because that's kind of where I was going. But the higher the entropy you have in your states, the more entanglement you have, the harder it is to visualize. If you have a proper single state determinant state, there is no entanglement, and in principle, you can say this is what the whole wave function looks like, this is what the electron wave function looks like, you can put them on top of each other. But as the entanglement grows, because it's a complicated system, I see why this doesn't work.
I mean, I wouldn't call it entanglement, it's just for me the normal Coulomb abstraction.
The entanglement is in the state, so it's a matter of slides.
Yeah.
Ask your questions at the same time in an entangled way, so we can steadily think.
Thank you for your presentation. I was wondering, you said that these excitons they form something like hydrogen-like wave function. What if you take a B exciton? Do you also get like hydrogen-like wave functions, or do those?
Okay. I just need a little bit more work to be more systematic on this. So in general, the more confined your exciton, the less hydrogen-like it. Now only for really very extended wave functions, this so-called Wannier mod picture starts to hold, and then it becomes more and more hydrogen-like. And so what is important in the hydrogen picture is that you have full rotational symmetry. That we don't have, but we have 3 or even 6-fold rotation axis. So it starts to be like angular momentum. We call it crystal angular momentum because it's only valid modulo the n-fold rotation. So for extended excitons, it starts looking like angular momentum, and like when you plot the wave functions, they look more and more hydrogen.
Stephen, and then we have a question online from Christoph.
I have a question. Can you hear me?
Yes.
Yes.
Hello, Christoph.
Okay. I have a question about your Bethe-Salpeter equation. You have there the kernel, which I suppose is, in your case, the bare interaction minus the screened interaction. But the bare interaction is misses the long-range component. Is that so?
So if we, I didn't put the formula, but it should be the bare Coulomb interaction. Sorry, the screen Coulomb interaction plus the bare exchange. And yes, if you go to Q equals 0, you, depending on how you do it, you may or may not take into account the long range interaction, and then you have to distinguish between the longitudinal and transverse exciton. Is that
Yeah, so I was wondering, that is the point that I was wondering, because you showed that you get a triply degenerate set of excitons in lithium fluoride, but you would get it only for the electron hole Hamiltonian without the long-range component of the Coulomb interaction.
Yeah,
But if you include that, then you break the symmetry again. Yeah,
yes,
because then you, instead of the triply degenerate set, you get a doubly degenerate and one state that is non-degenerate. And I was wondering, actually, it is those excitons that we should consider as excitons, I think, because they give the poles of the inverse macroscopic dielectric function.
yeah, that is correct for ears. I still think we are doing the right thing for the optics.
I mean, your excitons are basically then the nodes of the inverse macroscopic dielectric function and not the poles.
Okay, yeah, we can discuss this later. I mean, what you mean here is just that when you look at dispersion, that at the gamma point you would no longer be threefold degenerate.
Yes, exactly. And that breaks the symmetry. So that was actually my point, because you consider here the symmetries, and let's say the poles of the loss function actually break the symmetries again. Not the poles, sorry. This long-range component of the Bayer interaction breaks the symmetry in the end, even for the gamma point.
But only for the gamma point, or also elsewhere.
Well, it's like,
yeah, elsewhere it doesn't make much sense to consider the optical absorption spectrum, because that you only have at the gamma point anyway.
Yeah, I mean, as soon as you go away from gamma, you break it, as you say, and then it's like with the phonon dispersion. I agree. Okay, maybe
Come tomorrow. Christoph, come tomorrow.
Come tomorrow. Okay.
Of Ricardo, and we can discuss further.
He's not allowed to ask questions.
No, but to the jury.
So,
The question to the jury. I have the question.
since we all know each other anyway,
Yeah, come tomorrow, Christoph.
come to the defense, you can ask at the bottle afterwards.
Yes, exactly. Really, you have welcome.
Since we have a second talk coming up, I suggest we break here. I'm sorry, Stephen, but you're at the bottom, and you can also do your question afterwards. Which reminds me, let's applaud first.